Hey there, my name is Chris, and in this video I'm going to be showing you how to take captured audio in C++ and display its frequency makeup in the terminal. This is the result of the tutorial, and as you can see, my voice sits pretty low in the register, but whenever I use S's and sounds like that, the high frequencies bump up. Now, I like to explain the concepts as I go, but if you're just here for the code, I provided a link in the description to the GitHub repository that contains the final code of this tutorial. And if you just want to see the coding segments of this video, I've also provided chapter divisions for this YouTube video that you can use to jump just to the parts that you need. So without further ado, let's get into the code. Alright, so starting off in the code that we ended up with in part 1, I want to do a little bit of cleanup. The first thing is to change the link for PortAudio download. They changed the link to now use HTTPS, and it won't work if you leave it HTTP. And so adding that S there allows this target to work again. So in main.cpp, we have this function called PA_test_callback. This is the name of the callback function that PortAudio in its example documentation gives. We can give that a better name though, a more descriptive name. In our case, I think that can be stream callback. And in VS Code there, I did Control-Shift-L to update any references to this function in this file. And once I'm done with that, I can press Escape to go back to my one cursor here. Additionally, as I learned after making the first part, we don't actually have to define these output parameters. So we can get rid of this and pass as the output parameters pointer null. And so now you can use devices that don't have any outputs, and PortAudio will be able to handle that. Also, as you may have noticed in the last part, there's no new line printed when the program ends, and so there's kind of an awkward spacing issue happening at the end. So if we do printf new line just once at the end of the program, then that'll be solved. A couple more things now. I'm going to add a 0.0 after the sample rate, and this is going to aid in calculations later where we need sample rate to be a double. And finally, I'll define the number of channels as a preprocessor constant to be 2. And then I'll take number of channels and put it right here in my input parameters, because we're going to use this in multiple places, so we may as well parameterize it. All right, now we're ready to start. Now as a refresher, if I do make and /cpp audio capture, then we'll see the results of the last tutorial. This is a volume bar that listens to the audio that it's hearing and shows a simple volume bar based on the level of audio that it's hearing. So I figured I didn't explain it very well in the last video, and I'd like to explain what we plan on doing for this video to get the frequency data out of our samples. And so here I will explain a bit about what's going on. Let's say we have an audio sample. In our case, this audio sample is constantly being recorded. We have real-time audio, and little chunks of that are being passed to our program as we run it. In our case, we've defined the sample rate to be 44,100 Hertz. So 44,100 times per second, the computer is getting the sound level of the sounds that it's hearing at that one point. Once it gets 512 of these, it will store that into a buffer, and it will pass it to our callback function. And our callback function can then do whatever we need to with it. In our case, we take this waveform that we end up with, we take the absolute value so that we only have positive values, and then we take the maximum value that we see in that sample of 512 points to get our volume. Now let's say we want to get the frequency data of this waveform. We're going to leave it as is, and then we're going to pass it into an algorithm called the Fourier Transform. The Fourier Transform takes this sample of audio and figures out which frequencies make it up. From there, we will get a frequency breakdown of this chunk of data. The Fourier Transform actually works on functions in general. What we're going to be working with is a discrete Fourier Transform that allows us to take frequency data of a specific chunk of data. In our case, since we have 512 frames per buffer, when we take the discrete Fourier Transform, we're going to end up with half of that, or 256, points of data that represent frequencies. There are simple formulas to be able to derive frequency from an index or index of a frequency, and we'll see this later in the program. But for now, hopefully this gives you a good idea of what we're doing when we use this fast Fourier transform algorithm. So with that all out of the way, let's get back into the code. The first thing we'll need is a library that contains the algorithms that we will need to perform a discrete Fourier transform on our audio samples. In our case, we're going to be using the C++ library called FFTW. FFTW is a C++ library that contains algorithms that very quickly get this frequency data. So in the make file, we're going to install it just in the same way that we did with PortAudio. Their installation steps are very similar. One thing that we can do is split out PortAudio's install step and FFTW's install step. This is a good thing about make files, so that if I already have the PortAudio library installed, for instance, I don't need to install it again when I install FFTW. So I'm going to rename install deps, which stands for install dependencies, to install PortAudio. Same for uninstall. Above this, I'm going to say install deps, just as last time, and also declare that as phony since this is not an actual file. Similarly, I'll do uninstall deps. And now that I've split this, I can now say that install deps should run install PortAudio and uninstall deps should run uninstall PortAudio. Now we can list as many targets as we want after this, and uninstall deps, for instance, will run every single target that it sees to its right after the colon. So from here, we can copy these down and say install FFTW, and I'm going to take that and move that and copy that all around. Now we can say that install deps should install both of these and uninstall deps should uninstall both of these. What this allows us to do is to install or uninstall each of these tools separately. So in my case, I already have PortAudio. It's already in my lib folder. PortAudio can take a long time to download and install. And so if I don't need to do that, then I can just run install FFTW. So in the target definition or the recipe of install FFTW, not much changes, only two things change. One thing that changes is the download link to the library. This is going to be this link that I will have available in the description. And the other part of this is to add sudo make install. This will move the header and library files into the proper places that your compiler will be able to see when it compiles this program. And finally, we will need to change the reference to the lib/PortAudio directory to FFTW-3.3.10. Finally, in the uninstall step, similarly to here, we'll need to rename lib/PortAudio to lib/FFTW-3.3.10. And we are ready now to install these dependencies. So since I already have PortAudio, I'm just going to run make install FFTW. Now this takes a while, so I'm actually going to just wait here until it's done. At some point, since we use sudo, you may need to input a password, but I will be back when this is complete. All right, about 4.5 minutes later, that is complete. So I can now close my terminal and we can get into the final step in the make file, which is to tell the linker and compiler where to find the FFTW library. So the first thing I'll do is neaten this up a little bit. You can escape this line here and this makes things a little neater. And after this, I can add -I /lib/FFTW-3.3.10/API. Additionally, we'll need to do -l FFTW3. Back in main.cpp, we can pound include FFTW3.h. We're going to need to store some data between callbacks. This is going to be data that FFTW is going to use as input and output. And we actually have a way to pass data into our callback and persist it. This is what this void pointer user data is, and we didn't use it in the first part, but we will use it now since we have data that we're going to continually modify. So under these preprocessor statements, I'm going to say type def struct. We're going to fill in some parameters in a bit here, and then we're going to say that this type is called stream callback data. Under this, we can say that we have a static variable. It's going to be a pointer to a variable of stream callback data type, and we're going to call it spectro data. Now we can copy this and we can pass it to our PA OpenStream function call. Spectro data is just a pointer here, and so when OpenStream expects a void pointer, it sees a pointer and it says that's fine. So in our callback data, when we get this user data, we will need to cast it. And so we can say that a pointer to stream callback data, we're going to call that callback data, is equal to user data cast to that type. Now we can define what we're going to store in this variable. First thing we're going to do is define our two buffers that we'll use, that FFTW will need to do its calculations. They're both arrays of doubles, and so we're going to represent that as a pointer to a double. First one we're going to call in, the second we'll call out, and then we're going to store what is called an FFTW plan. We're going to call that P. Then we're also going to store two variables that are going to specify where we start and where we end in the frequency array that we get. We'll use that when we bound our frequency output in between two frequencies. So we can say int start index and int spectro size. Now above here, we can specify these bounds. So I'm going to define spectro frequency start as 20. This is going to be 20 hertz as our lower bound, and I'm going to make 2000 hertz the spectro frequency end. Now in our main function, we can define our stream callback data. So right before we query the number of devices, we can say that spectro data, which is our static variable located right here, is the result of a malloc. So we are going to allocate some data to the heap. That's going to be of the type stream callback data. It's going to be a pointer. And we're going to say malloc size of stream callback data. Under this, we can now define each of the properties that we have said will be stored in our callback data. First property is the input buffer, and just in the same way that we allocated data for our spectro data, we are going to say that this is going to be a pointer to a double, and instead of just one element here, we're going to say that this array is frames per buffer long. This expands to 512, so we're saying that we have a double array that is 512 elements long, and that is our input buffer that we're going to use with our FFTW algorithm. We can copy this and do the exact same thing for out, and it's always good to check if this was successful or if we maybe ran out of memory. So we can say if either of those are null, so we can say if spectro data's in is null, or spectro data's out is null, then we can inform the user. We can say could not allocate spectro data, and we can exit failure. But if we go past this point, then we know that we were able to allocate that data and we can move on. So now we can say that spectro data P, which is the FFTW plan that we saw earlier, equals FFTW plan And here we see all the different ways that FFTW can calculate the fast Fourier transform. You can find more information about all these different types of algorithms in the link in the description, but in our case, we will be using a reel-to-reel, one-dimensional fast Fourier transform. Now, creating a plan is going to allow FFTW to determine which algorithm it should use. It has many different algorithms that it could use, but it's going to use the best one for our use case. The plan defines how it's going to go about doing the fast Fourier transform. Now it expects a few parameters here. First one is n, or how big our sample data is going to be. Next is the input buffer that FFTW is going to pull data from. Out is the buffer that is going to write its Fourier transform data to. Kind defines the output format that we want, and the flags will define how it creates this plan. Now, what's worth noting is that the input and output buffers are passed in here once and never asked for again. So FFTW expects these buffers to stay exactly where they are as long as you use this plan. We can say frames per buffer as our input size, spectrodata in as our input buffer. I can tell this line's going to get long, so I'm going to break this up a little bit. Spectrodata out as our output buffer. Then the kind is going to be FFTW underscore R2HC, or real to half complex. This means that the first n over 2 elements will be real numbers, and these are the numbers that we want. These are the values of the frequencies. The second half of the resulting array will be the corresponding imaginary components of the numbers that it spits out. This again goes into how the Fourier transform works, and if you'd like more information about that, there are tons of resources around on YouTube. For now though, we're not going to be using those imaginary parts. We're just going to use those first n over 2 elements in the array. Finally, we'll need some flags, and in our case we can just do FFTW estimate. Now at the end of the main function, we can clean up our data that we allocated. So whenever you have allocation up here, you are always going to want to free it elsewhere in your program. So from the documentation of FFTW, they mention that this function allocates memory. FFTW will also provide a function to deallocate any information that it created for that. So we can see FFTW destroy plan, and we can pass in that plan that we created before, which is spectrodata P. Then we can FFTW free the input buffer and the output buffer. And finally, we can free spectrodata itself, which we allocated in this first line. Now we have 2 parameters left in spectrodata. We have start index and spectro size. These are going to be using the preprocessor variables that we defined up here and the short formula that I mentioned before that can tell us which indices correspond to which frequencies. Ultimately, we just want our data that we see to be all the frequencies that we got between 20 Hertz and 20,000 Hertz, which is roughly the range of frequencies humans can hear. So first, I will define a variable that will be used in the calculations of both the start index and the spectrogram size. This is going to be a double, and it's going to be called sample ratio. And we're going to say that's frames per buffer divided by sample rate. Now this is why we defined sample rate as a double up there, because if this were left as 44,100 without a decimal place, then this whole thing would evaluate to 0, because this would be integer division, since both of these would be integers, and our sample ratio would always be 0. So by having one of these as a double, or alternatively, I could have cast this to a double if sample rate were still an integer, then we have a double on one side of this operation, so the whole thing is interpreted as real number division. Under this, we can say spectrodata's start index is going to be sample ratio times the spectral frequency start. So the spectral frequency start, 20 Hertz, times frames per buffer divided by the sample rate is going to give us the index of 20 Hertz. Now we're going to need this to be an integer, And right now, this is going to chop off the fractional part of this result that it gets and store it in the start index. Oftentimes, and in this case, you'll see this is going to be a very low number. In our case, it's going to be below 0. So when it chops off this fractional part, we're going to get 0 as our start index. This is fine, but in the result of a Fourier transform, the start index is not very useful to us, since it's basically the bias of the signal or a flat line that's added. And we want frequencies. So when we get our output data, what I like to do is surround this with a function called ceiling. And we will need to up here include cmath. But this is going to take the number that we get here and move it up to the next integer greater than or equal to this number. In our case, this is going to be 1. Under this, we can define the spectro size. And we're first going to calculate the index of the n frequency. And this is going to give us the last index in the output array that we want to be in our range. To get a size from that, we can subtract the start index. Now say our frequency is a bit too big and this number goes past n over 2. We want to avoid this. And so we can surround this with a min function. Now cmath doesn't actually have a min function, so we can define one up here. It's very similar to our max function that we made in part 1. The only difference is that it's called min, and we're going to put a less than there in that ternary operator. And that's going to give us the minimum of the two values we pass in. So I can say minimum of, and this line is getting long, so I'm going to split this up, the minimum of the value we just calculated, which is the index of the frequency that we want, and the actual value of frames per buffer divided by 2.0. So that should be all for our main function. Now all we'll need to do is update our callback function to calculate and display the frequency data that we'll get from our waveform. The first thing that we can do is remove the calculation that we did in part 1. We can keep all of this first part. We can remove all the way up to flushing to standard out. And now we have a blank slate to start working. So the first thing we'll need to do is move our audio sample into the FFTW's input buffer. Up here, we've defined in as the input buffer that we get from the stream callback cast to a float pointer. And as we defined earlier in this video, our frequency data input buffer is going to be stored in this callback data variable because our user data is pointing to what we passed in here, which is our spectro data. So to move our audio sample into our input buffer, we can notice that they have the same size. Input buffer is defined by frames per buffer in its length, and so is our callback data's input buffer. So we can iterate over this size. So unsigned long I equals 0, I is less than frames per buffer, I plus plus. And inside here, we can say callback data's input buffer at I is going to be set to our audio input buffer at that given spot. Now our input buffer has multiple channels, and as I described in the last video, these channels are aligned next to each other in our input buffer. In our case, we have 2 channels. For the purposes of this tutorial, we're just going to be looking at the audio sample from the first channel. We can accomplish this by indexing at I times the number of channels. And so when we index at 0, we're going to get 0. When we index at 1, we're going to get 2, which is the second sample at the first channel. So on and so forth, it'll stay at that 1 channel. If you want to get to another channel, you can provide an offset. So if I wanted to get to the second channel, I could do that. In this case, I'm only going to be looking at the sample data from the first audio channel. So now that that's all copied in, I can run FFTW execute, and I will just pass in the plan that's stored in the callback data. And now, once this is executed, the output data of our callback data will now contain the frequency data that we want to use. So now all we need to do is display that data. The first thing we can do is iterate over the display size. I've said that the display size is 100, and in my case, what I'm going to do is over these 100 characters, I'm going to sample the data that I get out of the frequency data, and I'm going to display each character as a full block character with its height dependent on the value of each element. So I'm going to say for int I equals 0, I is less than this display size, I plus plus. First thing I can do is get the proportion that I am through this output. So I can say double proportion is equal to I divided by display size. Now again, when I run this, I'm going to always get 0 from this because I is always going to be less than display size, and because these are both ints, this is integer division. So I can cast this to a double, and this solves this. I'll be doing real number division, and proportion will be the correct value. From here, we can sample our data by doing essentially a linear interpolation from the start index to the end index. So we're going to say that our frequency, which we can store as a double, is equal to our callback data output buffer at a given index. This index will be callback data start index plus proportion times callback data's spectro size. This is going to evaluate to a floating point number, and so we'll just need to cast that as an int to be able to use it as an index to this output buffer. Again, this line is pretty long, so I'm going to break it up a bit. So now we can determine from this frequency data which character we should print. Now in the description, I've put 8 levels of block characters, which increase in height by increments of 1/8 of a total block height. So if we see a value that's less than 1/8, then we can show the smallest character, for instance. And as we see values that get higher and higher in increments of 1/8, we can show the next character in the series. So here's how we do that. We can say if the frequency is less than 0.125, which is 1/8 in decimal form, we can printf that character. And again, I'm going to leave these in the description, but this is going to be the smallest one for now. And now we can say else if the frequency is less than 0.25, which is 2/8 or 1/4, we can show the next one in the series. We have 6 more characters, so I'll just paste this 6 more times. Next in the series, we have 375, 0.5, 0.625, 0.75, 0.875, and at the end here, we can just say else. So these gradations here are saying if it's less than 1/8, if it's less than 2/8, on and on until it's less than 7/8, we'll show the second to last character. And if it's any bigger than 7/8, then we'll show the full block character. I'm going to paste these characters in real fast. And there we go. We have our characters there, and they will be printed according to the frequency that we see at each point in the output buffer. Let's see how this looks. So the first thing we can do is just run make, and that will link and compile our program. As we can see, we got no errors, which is an amazing thing. And then we can run /cpp audio capture. So for now, it's capturing my mic, and you can see for high frequency things like the S's that I say, the high frequencies of the bar are showing. I'm actually going to go into the main function and say that I'm going to run this program for 30 seconds before it ends so that I can explain this a little better. So you'll notice that a lot of the frequencies are piling up at the bottom. We're not seeing a lot of data happening on the right side of this frequency bar. This is because frequency happens exponentially. 2 C's on the piano are the same note, but one is an octave higher than the other. Each octave jump is equivalent to twice the frequency. But on the piano, we kind of visualize these sounds spaced linearly. So what we can do is sample this data logarithmically or exponentially to show this data as spreading out the data at the bottom and condensing the data at the top to resemble more how we experience sound. So what we can do here is observe that the values that we're getting for this proportion are always between 0 and 1. Now, when you take a power of that number, so let's say 0.5. If you take 0.5 squared, that's 0.25. If you take 0.5 cubed, that's 0.125. As you can see, these numbers keep getting smaller as we multiply them by themselves. And we end up with this exponential curve on the range from 0 to 1 if we take these numbers to a power. If we sample our data this way and say our proportion is equal to the linear proportion taken to the power using the standard power function of 4, for instance, then we are going to shrink down those first values to very low values. And then the higher values are still going to go up until they're 1. So the full range is still covered, but we're starting off much slower. If I make and run this again, then you'll see that the lower values are much more spread out here. And in fact, a lot of these are sampling the same exact point in the array, and a lot of these upper frequencies are actually undersampling what we have. They're kind of interspersed throughout the actual buffer that we have. Now, if you want, you can apply some averaging functions so that you actually still get all of this data. Maybe you want to add everything together, or you want to average them together in order to get these sample points a little more obvious in the output. And you can also use smoothing algorithms to make sure that this output data looks a little less jittery, for instance, if you want to display it. In my case, I've used this method to print audio data to an LED strip of mine. I use this frequency data to drive the hue and the value of colors on the LED strip to real-time audio coming from Spotify on my Raspberry Pi. And really, when you discover techniques like this, opportunities and applications open up everywhere. So I'm excited to see where you take this information and what you do with it. Please post in the comments if you have anything cool that you want to share. And other than that, that is the conclusion of this small series on how to capture audio in C++. I hope you learned something. And again, if you would like to see the final code with comments written all through it, I provided a link to the GitHub repository in the description. Thanks for watching, and happy coding.